Hello and welcome to our second video on convective turbulence. In the first video, we went through the definition of convection, and also we talked about the thermodynamics of the atmosphere and how free convection occurs. Now we're going to talk about the characteristics of thermals. In the previous video, we talked about parcels of air rising through the atmosphere. We give these parcels a special name. We call them thermals. And thermals are simply buoyant, rising parcels of air or bubbles of air. There's actually two different models for thermals. We talked about bubbles, and we'll look at those in a little bit more detail. But scientists also have discovered that thermals can be plumes or columns. They're also sometimes called jets. And this is where the thermal, the rising bubble of air or rising plume of air, is actually attached to the surface. In other words, there's a continuous updraft that's being generated by a hot spot on the surface that causes rising air. And that rising air is continues all the way up through the atmosphere. There's no breaks in the plume. Scientists have also discovered that sometimes thermals can be just bubbles by themselves, where they're heated from the ground or there's instability that causes them to rise. And these bubbles are not attached to the surface, they're not continuous, so they rise on their own. Sometimes they're also called vortex rings. Notice that in the center you'll see a strong updraft, but along the sides you'll see downdrafts and also some circulations within the thermal. So that's what scientists have found flying through thermals over the years, that there are downdrafts, typically weak downdrafts along the edges of the thermals, but in the center or the core of the thermal, you'll get a strong rising motion anywhere from 200 to 2,000 feet per minute. Thermals tend to expand as they rise. Of course, air pressure is less at higher altitudes, so the parcel of air actually expands. And the width of the thermal is on average typically 1/4 the height of the thermal. So at the surface they'll be rather narrow, only about 100 to 300 feet across. But at 4,000 feet, if it's 1/4 the height, that means they'll be about 1,000 feet across. So the higher they go, the wider they get. And then the height depends upon the height of the thermal, how high it goes, depends upon the temperature profile of the atmosphere. In other words, thermals continue to rise as long as the temperature inside the thermal is warmer than the environment or the surroundings. Inside the thermal, if it's warmer, it means it's less dense than the surroundings, and it continues to rise until a point where the temperature of the parcel equals the temperature of the environment. At that point, since the temperatures are equal, that means that the air density inside the parcel or the thermal is equal to the air density outside. So it's not buoyant anymore. But the parcel or the thermal does not stop there. It has momentum. It will continue above that point, and eventually the air becomes cooler aloft, the parcel of air comes cooler aloft, and it will start to sink. And this is what you see during the summertime. If you watch the tops of cumulus clouds, they appear to bubble. And that bubbling is a result of the thermals rising above the point where the temperatures are equal, and then rising a little bit higher until the air in the parcel becomes colder and sinks again. So that bubbling is a result of the air overshooting the equilibrium temperature and then coming back down to the temperature again, the equilibrium temperature. Also, thermals tend to advect or move with the wind, so that they'll be carried downwind, and they also elongate with the wind. That's your second video on thermals. The next one we'll talk about what causes the instability.